Okay, hello everybody. I hope you are enjoying so far the BigScience episode 2. We're going to continue with this next session with the same mix of deep dive of some of the stuff which is happening inside BigScience, together with together with talks from other cooperative large initiatives. So this first deep dive is going to be around the prompt engineering group. They did some very successful hackathon beginning of the year, and they're going to share some of the findings they have started digging out thanks to this hackathon. So Victor, it's all yours.
Thanks, Matthias. So hi, I'm Victor Sanh, and together with Stephen Bach and Albert Webson, we're going to present the latest updates in the modeling prompt engineering working group. Unfortunately, Colin Raffel couldn't join us to give the presentation today. But more specifically, we're going to talk about zero-shot generalization and how multitask fine-tuning enables some sort of zero-shot generalization. So first, I'm going to talk about T5, a previous work from Colin Raffel and colleagues at Google that was released almost 2 years ago. So T5 stands for text-to-text transfer transformer, and T5 is basically a pre-trained model, like trained on a very large corpus called C4. And the key point of T5 is that it unifies a lot of different tasks in natural language into the same text-to-text format. So what I mean by the same text-to-text format is that when you consider standard tasks like machine translation from English to German, then the input would be a sentence or document in English, and then you would ask the model to output its translation into German. So that is good, and that it's good. So here you give the input in English, and then you output the sentence in German. But you could do also something very similar for something even fancier like classification. So usually in classification, you would expect the model to output labels like 0, 1, 2, depending on the classes. But here in the text-to-text format, you give an input and you're also generating the label as a text. So this example is from COLA, the Corpus of Linguistic Acceptability, whose task is to decide whether a sentence is grammatical and sensical. So here the input is the course is jumping well, and this is not sensical, so the output would be not acceptable. For other tasks like sentiment classification, for instance, you would give a movie review and expect the model to output negative or positive depending on the sentiment in the movie review. You could do also something super fancy for regression tasks, for instance, for STSB, where the task is to output a score between 0 and 5. And here the model has to generate the score between 0 and 5, but as a text string. So here it's 3.8. And finally, for abstractive summarization, the task is to extract some span of text in the input as the summarization. So literally copying some of the input to the output. And into this unified format, basically, you can cast and frame all the tasks in natural language. You give the input to a model, and you ask the model condition on this input to generate some response to the input. And so from a practitioner side, this kind of unified framework kind of simplifies a lot of the assumptions and a lot of the choices, especially on the hyperparameter and how you do fine-tuning. So like in the standard transfer learning setup, you take a pre-trained model and then you fine-tune. But recent works have shown that there are a lot of choices that are involved in this fine-tuning step. How do you initialize your classification head, whether or not you have to throw some of the layers, which layers you throw, how do you initialize these layers, do you have to reinitialize these layers? the advantage of this unified format is that everything is framed into the same setup. It's the same model, same weights, and so a lot of the hyperparameter search are basically condensed to only one architecture in one setup. And obviously, this kind of framing into a single task is not new. This is an example from a paper called DK-NLP from 2018. And in this benchmark DK-NLP, they frame 10 different tasks into the same Q&A format. So they frame summarization, translation, natural language inference, sentiment analysis, etc., into this same question answering format. So for instance, if you take the task of machine translation, then the question would be, what is the translation of the following sentence from English to German? You would give then the sentence in English and the model would output the sentence in German. And at that time in 2018, this benchmark was considered very, very hard, even though that was before all the craziness around pre-training large language models. And more recently, we are pretty much all aware of the GPT-3 model, which is a very, very large language model trained on a very, very large data set. And the key point from GPT-3 that surprised a lot of people in the community is that the model is able to perform a lot of different tasks in a non-trivial performance without any kind of supervision for the task at hand. So everything is like kind of framed into this text-to-text format, but in a zero-shot way. So you kind of condition the model on some task instruction, translate English to French, then give you input, and again, it would output the label or the expected output in a text format. And kind of like the key idea in the GPT paper is what they call in-context learning. So the assumption is that you don't really need, you can take the model as it is, so pre-trained, and without doing any gradient updates to the model is able to perform a lot of different tasks in a non-trivial way without seeing any kind of explicit supervision for the task at hand. So in the paradigm of in-context learning is where you give some examples of the task at hand. So let's say addition, translation, or grammatical correction. You give a few examples of the task at hand and also a description of the task at hand in natural language. And by conditioning on the natural language instruction and the examples, the pairs of examples, X, Y, you frame everything as a text, but more specifically, everything is framed as a language modeling problem, and the model is able to perform the task without any gradient updates. And in-context learning sometimes work less well than the fine-tuned state-of-the-art model, but there are some cases where it works really, really well, and that was, I guess, one of the very surprising thing in the community. People thought for a long time that you kind of need kind of explicit supervision for doing tasks at a very high level. And this is an example for Trivia QA, which is basically literally a QA data set, but framed into trivia questions. And we see that GPT-3 in a one-shot or few-shot setting is able to outperform the fine-tuned state-of-the-art at that time, without any gradient updates or explicit supervision for that task. And so now the question becomes like, why does in-context learning? So why does in-context learning kind of work so well? And one of the hypotheses is like in-context learning and the huge pre-training is kind of like the driving force here. But another hypothesis that we want to consider here is that this large language model is just a very, very good multitask learner. So in the sense that if you kind of scroll the web, you are able to dig up these kind of web pages. Here it's an example for Scary Mummy. And you see in this page that basically have question answer pairs. So in what year was the first ever Wimbledon championship held? And then you would output the answer, 1877. And so this is an example, a direct supervision for Q&A. But you could also imagine some weak supervision for tasks like sentiment analysis from website of review. So like you have a product review and then a rating between 1 and 5. So the hypothesis is here that the language model pre-trained on the very large corpus received a lot of weak supervision for a bunch of different tasks framed as natural language.
So this alternative hypothesis points to a question that's growing increasingly prominent in recent work, that what are the potential benefits of an explicitly supervised multitask objective as a complement to the traditional or becoming traditional unsupervised language modeling objective. And so our work as part of the BigScience group falls into this category, and we also want to highlight some of the other great work in this area. So one related work studying multitask learning is this work on unified QA. And what they did was they took a T5 model and trained it in a multitask fashion, or fine-tuned it in a multitask fashion on many different formats of question answering: extractive, abstractive, multi-choice, yes, no, etc. Next slide, please. And what's really interesting about this work is how well it does on data sets that were created after it was trained. So this is one example where these folks created a data set asking questions about different academic subjects up to the high school level. And what they found was that unified QA, even though it hadn't been trained on any examples from this particular data set, could significantly outperform this much larger GPT-3 model. And you see that it does, on average, 5 percentage points better in terms of accuracy, suggesting that this multitask training is helpful. Next slide, please. And there's been some other recent work in this area. So on the left, some recent work cast many different types of tasks, traditionally supervised tasks, into a prompted format where the data is expressed in natural language, and they trained it in a multitask fashion on many different types of tasks and found generalization to new held out unseen tasks. Also related is this recent benchmark called CrossFit. Now this is for the few shot setting, but what they found was that multitask learning again can be helpful in adapting to new tasks, generalizing to new tasks that haven't been seen before. Next slide, please. And then very recently, in the last couple of weeks, there's been this paper that came out from Google Research where they created a GPT-3 scale model called Flan, and first pre-trained it with a language modeling objective, an autoaggressive, trained an autoaggressive language model, and then fine-tuned it on, again, with a multitask objective on many different tasks expressed as natural language. And so what they find is that this 137 billion parameter model significantly outperforms GPT-3 in the zero-shot setting, and approaches and sometimes even surpasses GPT-3 in the few-shot setting. Next slide, please. I think we skipped one. Can we go back? Perfect. So, so then this, leads us to kind of what we've been working on in the BigScience group over in our group within the BigScience project over the past 6 months or so, kind of concurrently exploring a lot of these questions. And we initially set out kind of phrasing this as, can we obtain a model that can readily perform tons of NLP tasks, especially tasks that we haven't seen before, and do it at a high level. And so we set out to train a big model in a massively multitask setup with an extremely diverse set of task formats. And so the emphasis is on, or one of the emphases is on kind of the diversity with which we express these tasks. So as you recall from T5, there's kind of these codes, these prefixes in the beginning of the prompts that sort of say what the task is. In these zero-shot settings, we have to describe what the task is. And so there's kind of a lot of open questions around how we actually describe what we want the model to do. And so to study this, we took advantage of one of the big benefits of being part of BigScience, which is a massive community. And we held a hackathon and brought a community of people together to all write different templates for expressing different tasks as natural language. And we used, we did this for many different supervised data sets, or traditionally supervised data sets. Next slide, please. So this is an example of the interface that we use to, during this hackathon, we call it prompt source, but what you see is that it lets users take on the left side data that is in kind of a structured format and write a template for expressing it as natural language. So here you see for MRPC, they can create placeholders for the different pieces of data and express how that should be presented as a natural language prompt. And they can also do things with like little bits of scripting to kind of create more interesting variation. Next slide, please. So this was a great success thanks to all the participants. We've created prompts for over 160 data sets, and we have 1,800. It's actually more like 1,900 now templates in this corpus that we're calling the Perpetual Pool of Public Prompts, or P4 for short. And this leads to over 100 million examples in 100 million examples of prompted tasks. Next slide, please. And just to show you a little bit more about what these templates look like, and to kind of illustrate the different ways that people can use them. Here you see for the same paraphrasing task, different ways that people can express them. So on the left, people present kind of the two pieces, and then in a sort of formal way say, pick whether these questions are duplicates or not. And on the right-hand side, it's more like sort of this, first-person situation, like, can you help me with this task? Next slide, please. And this leads to this pattern kind of plays out across many different tasks. You can see the same thing here for summarization. Next slide, please. And also extractive question answering, again, where users describe in this templating language how the different pieces of the example in the underlying data set should be expressed in a natural language format. Next slide, please.
Okay, so with all of these amazing data sets and prompts that are created by our volunteers and collaborators at BigScience, what research questions are we going to do with these data? So to make our research questions precise, we actually need to clarify a term that has been a little overused in machine learning called generalization. It's a term that has now bestowed with many, many meanings just because we are now doing so many massively multitask training. So it has at least 4 sense for the purpose of our paper here, and they correspond to like 4 different research questions, and each row is a different level of generalization. And at the top row, what you have is what basically machine learning has always done, which is it's the same task, same data sets, but instead you hold out some instances from training, such that when you're evaluating on these unseen instances, these unseen examples, that you're making sure that your model is now just memorized in the training set. But if you go more and more level of generalization on the second row, perhaps you evaluate on unseen examples, but you also evaluate on unseen prompts. Now, this is actually enormously interesting research question currently in the literature, where we see that existing prompt-based models are sort of fussy about the prompts they see. Sometimes you change one single word or a single punctuation in the prompts, and the whole model fails. It doesn't work anymore. And one of our core research motivation is that, okay, but if we train on many prompts, 1,800 of them to begin with, then perhaps the models will learn to be more robust and learn to actually be semantic invariant to those surface form changes as humans would. And if we go one level next on the third row, perhaps you can also generalize to new domains. Now, this question actually has been answered a lot by the previous works that Steve just discussed, like unified QA, text embedding, CrossFit. For example, they will train on squat and then evaluate some grade school science questions, even though they were never trained on grade school science questions. This kind of domain generalization is another one. And finally, perhaps on the fourth row, what we are really interested in, one research question that's almost unexplored territory is whether you can generalize to new skills. Now, skill is a very difficult to define term, and it's very hard to define in cognitive science as well. But for the purpose of this talk, it just means that it's sort of a task category is conventionally recognized by NLP. So, for example, summarization is a skill or a task. NLI is a skill, and QA is a skill. And QA is a little fussy, but you can ask me more questions and gather down later. So if we say train massively many different tasks and skills, but if we completely hold out, say, NLI, can models still nevertheless generalize to a skill that has never seen before through the virtue of seeing prompts? Now, this is a brand new research question because we are sort of testing that if by training on 1,700 prompts, can our model learn to truly understand the meaning of prompts such that if you take the prompts like that describes what the task is, some sort of instructions, if you have this meta ability to understand instructions, then perhaps you're able to acquire new skills much more quickly. And that is a uniquely human skill, uniquely human ability that we aim to study in our research question. So next, please. Next slide, please. Wait, sorry, did you jump? Go back one. Yes, this one. Thank you. So to study what kind of a skill can you generalize to, we first need to categorize existing NLP data sets into categories or tasks or skills so that we can make sure that which one we can hold out. Now, this is a very delicate business. And again, you can feel free to ask me more questions. And this graph is only meant to be a simplification, and you can ask me more questions later. But very quickly, we basically took all the data sets that were studied by previous papers on multitask training. So unified QA, CrossFit, and task embed. We take all of their data sets, we filter out some ones based on very conservative categories. So very conservative criteria. So if it uses non-human language, then we filter it out. But we basically included as many as possible. And we also referred to all the data sets that were considered by the BigScience evaluation group as well. So we take all this pool of data sets. I basically read through all of them and then make a category that correspond to conventional categories as recognized in the NLP literature. And now we pick NLI as our pilot experiments as our novel skill, not simply because it's enormously useful for linguistic diagnosis, but that NLI is a very special laboratory task in that NLI is a task that humans are never explicitly trained on either. Like if you just grab any random adult on the street and you ask them, here's a premise, here's a hypothesis, does the premise entails the hypothesis, or is it neutral, or is it contradiction? That is a task most adult humans, unless you're a linguist, has never been explicitly trained on. And nevertheless, more normal adult humans find it extremely normal and easy and natural to respond to those questions, entailment or contradiction and neutral. So that is to say, adult humans find it very natural to perform zero shot on NLI, despite the fact that they were never explicitly trained on. So that's what motivated us to choose NLI as our unseen held out skills for evaluation of our model. Next slide, please. And here's our model. We call it T0, which is T5 zero shot. The important details is there aren't that many important details except that it's 11 billion parameters model. It's 10 times smaller than GPT-3 and Flan, but it is able to outperform them in many different aspects, as I will show soon. It's trained on 75 data sets so far. That's all the ones we showed in the previous slides, and about 700 prompts of them. Most of those prompts are manually written by our amazing collaborators in BigScience and manually reviewed by the 4 core co-authors. And all of those prompts will be released. In fact, technically they're already public, but you'll be able to use them very, very soon. So if we train on 700 prompts, does it actually work? Next slide, please. And the short answer is yes. Here's a sanity check. If we compare T0, which is the red one, that's the massively multi-prompt one, comparing that to T5, the blue one, which is zero shot, but not trained on these 700 prompts, then we see a gigantic performance jump, as you would expect. And most importantly, T0, the multi-prompt one, also nearly match the single fine-tuned baseline, which is if you take the same T5 checkpoints, if you just train one single prompt and train on the whole data sets. And we almost match that performance in basically all the data sets. So that's a very encouraging sign that this massively multi-prompt model does not catastrophically hurt performance in that our model capacity is large enough. Next slide, please. So this is a sanity check that we successfully passed, but here's a research question that we are really, really interested in. This is the 4th level of generalization, whether it is able to generalize to new skills through the virtue of perhaps some meta ability to be robust or understanding prompt instructions. And here we also see very encouraging results. In fact, a new state of the art, I will show you. So on the left, we see RTE, which is recognizing textual entailment. It's the NLI set in superglue. And again, the red one is T0. T0, again, it's zero shot. So it has never seen any NLI examples, NLI data set ever. But it is able to beat GPT-3. So in our zero shot settings, it's able to beat GPT-3 in few shot settings. That is few shot they do in context learning. And that our model is 10 times smaller than theirs. So that is a very encouraging result. It doesn't quite match the fully supervised model where like if you just train the whole 2000 training examples on RTE, but that is to be expected. And on the right side is our new state of art on ANI. This is adversarial NLI. It's the latest installment after SNLI, MNLI. It's universally recognized to be extremely difficult set. Even the state of art supervised model are at like 50-something%. And once again, we T0, our model, the red one, is able to outperform GPT-3 even in few shot settings, and even though they have a 10 times larger model. And if you caught up with the literature on Flang, we actually also outperform Flang a bit, and Flang is also 10 times larger than our models. So whatever we did here, it seems like we did something right in that through the virtue of training on many prompts, even though we have never seen any NLI prompts so far, it is able to generalize to this new skill or new task in a zero shot format. So all of that is quite encouraging, and our upcoming, these are all still preliminary results. In the coming up experiments, we will revisit all the other level of generalization, especially level 2, where we want to see whether it generalized to new prompts. So we will do more analysis on what kind of prompts tend to perform well and what kind of prompts tend to transfer well to novel prompts. And that's basically it. Next slide. So we would love to have more volunteers to help us because, as you've seen, we have 75-something data sets. I'm not experts on all of them. In fact, I'm only experts on NLI. Maybe experts is a big word. So we would love to have volunteers to help us to analyze these prompts and these data sets. Why do they perform well? What kind of instructions you need to do well on those data sets? And all of our prompts, again, will be released. It's in fact already public. And we'll also release our model checkpoints. So you can basically just download the TFAC checkpoints and either use our prompts or use your own prompts. And it will probably do pretty well on a novel unseen task, just like ours do on RT and ANI. So thank you very much. I hope to see you soon in the Gathertown.
Thanks all three of you. And as mentioned, there will be a round at the Gathertown at the end of the session. So I propose to you to start with the second deep dive of a working group of this session, which is the engineering one. They're going to tell us a bit what they did when they started burning some of the million GPU hours we have. Julien and Is are doing this, and I believe Julien is starting. It's all yours.
Yes, thanks. Just a correction. We are actually the architecture and scaling group, not the engineering, but we are quite close with them. So I can understand that what we are doing is fairly similar. And actually, some of the results that I will be discussing are very have been obtained by the engineering group. So that ought to be interesting. Anyway, I guess you can see my screen now. If I don't see any complaints, I will get started. So hi everyone. My name is Julien Launay, and I'm today with Beltagy, who will join us for the second part of this talk. And we are the chairs of the architecture and scaling sub-working group in BigScience. And today we are going to present to you the work we have done so far, and in particular under the angle of you only train once, making architectural decisions for a 100 billion model. The idea is that of this talk is that, okay, BigScience wants to build a 300 billion something parameter model, so a very large one. And obviously we are not going to be able to train like 5 of these, like that wouldn't be possible, let's say not only in terms of like GPU hours, but also of human time involved in doing this. So we have to make architectural decisions on smaller models and then make sure that they will scale to the bigger model. And that's the entire problem of our working group. So we are the scaling and architecture sub-working group. Our goal is to draft and validate an architecture and training setup that allow us to get the best out of the BigScience GPU budget. To do this, we are looking at establishing principal baselines, evaluating novel modeling choices. So like when something is not clear in the literature, or when we want to do something new that has not been done at like the 10 billion or more scale, we want to be evaluating it and checking how it scales. And this is like the scaling of candidate architecture. This is a very important aspect, because BigScience is an extreme scale project with a final one that is in 200 billion parameters. So we need to make sure that the decisions that we are taking, and the architecture that we are recommending will work at this scale. And we are working that what we do needs to be proven. Like we cannot take unnecessary risk. If we take if at the last minute we change something in the big one and we waste 4 million GPU hours, we'll not be looking very smart. The second thing is everything we do needs to be scalable and efficient. And once again, that's an issue of scale. Like the final one will consume something like 4 million GPU hours. So we cannot afford to waste some of that. Like even a 5% change, let's say in like your GPU throughput, how efficient you are, even 5% change is huge at this scale. So we have to be scalable and efficient. Another aspect is that BigScience is a multilingual endeavor. So we have to support multilinguality. And as we will see, that's quite a big unknown. And finally, there is all of the question of emergent properties, which has been talked, I think, a bit earlier in a short talk, of kind of like, okay, these big models are kind of special in some ways, and some of this is like few-shot capabilities, prompt tuning, that kind of stuff. And we want to keep the door open to this. So this talk will be structured around 3 of the main unknowns in BigScience and how we are trying to tackle them. So the first one is scale, because very few models have been trained in the 100 to 200 billion range. Essentially, you have GPT-3 of OpenAI, Jurassic 1 of A21 very recently. You have HyperClova in Korean of Naver, and Pengu Alpha in Chinese of Huawei. And none of these models have been trained in the open. So you don't have actually that many technical and training details in the papers for these models. So there is no open knowledge of how to train this very large model. And essentially, BigScience is figuring out this knowledge and making it out in the open. So it's a very interesting endeavor. And this is in total cooperation with the engineering working group. The second part is multilinguality. There is very limited knowledge on extreme scale generative multilingual models. This is because, okay, we have T5, for instance, we have MT5 with 100 languages and 11 billion parameters, but T5 is not purely generative. There is no large purely generative model. And this is an unknown that we have to kind of explore and to tackle. And finally, there is a question of something that has been called in the literature the curse of multilinguality, which is this question of, okay, can we make a multilingual model that will not severely underperform monolingual counterparts? And we'll go a bit more on this. And there's quite a few groups that are also working on multilingual aspects that are supporting us in this endeavor. And finally, the last question we are looking at is the architecture. And a big kind of moonshot that we have is to bridge a gap between encoder-decoder performance, a model like T5, and language models like GPT. Because we know from the T5 paper that there is quite a big gap, and prefix LM seems to be a promising way to bridge that. And so we we want to kind of try that and see if we can do this at scale. So these are the three main topics that we are going to go through in this talk and what we think are the three biggest challenges in BigScience. To look at all of this, I have to talk a bit about evaluation, because how do we evaluate what we are doing? So the basic one is like to just look at the simple metrics, the usual suspects: validation loss, your GPU throughput, obviously, because this is important. As I said, efficiency and stability are very important to us for the training of the final model. And then we have another tool in our pockets, which is why we are called the architecture and scaling group. This comes from this. It's empirical baking of scaling laws. So scaling laws are somewhat, I wanted to say recent, but at the speed at which things are moving in machine learning, it's not recent anymore. Now it's like completely normal. So if you don't know about it, scaling law essentially say that using simple power laws, using simple relationship, the performance in terms of validation loss of a language model is like you can predict it using simply the number of parameters, the compute budget that you have, the data set that you are running, and that kind of stuff. So this is work by Kaplan at OpenAI. And you can see it here essentially. If you train increasingly larger models, so each of these curves is a model that you are training, and this is your loss and here your compute budget. And you can see essentially that there is this, you want to always stick to the bottom left because you want to have the lower test loss for the lowest compute budget. And you can see that there is this optimality font, this Pareto frontier essentially, of like this optimal point where you want to be. And this is a scaling law that you see here. And this is a very simple power law, very simple relationship that you can establish. And this is a very useful tool to study how an architecture will scale, because you can establish this at the like 1 billion scale or even smaller. And it seems that this holds across scale, like GPT-3, for instance, fits on the prediction of scaling laws that were much earlier from GPT-3. Large models of what we are doing, so we are training in the 1 billion scale, essentially, for our baseline experiments. Something else we are looking at is a zero and few shot performance, because the modeling loss is not everything. The autoregressive loss is not everything. We also want to look at the zero few shot performance. So currently we are using the EleutherAI evaluation harness for English baseline, but we are looking with the evaluation group and especially towards multilingual evaluation, which I will talk a bit about after all. One being unknown in the evaluation and in our work is how the final 200 billion model will be used by the community. So we know that with weights of loading and streaming, stuff like zero infinity, which you have probably heard about, you can essentially infer any model on a single GPU. Like essentially, you can even infer a 1 trillion parameter model on a single GPU. But it will be very slow and still very expensive to run, essentially, in terms of compute. So if you look at what's the big, how the current big models that I talked about earlier are served, so OpenAI, A21, or Cohere, they are served through a hosted API with a text or log probabilities interface. And there is not really fine-tuning offered for the big models. So this might be a way how people will use the BigScience model with only text and log probabilities, which is essentially a few shot setting. But we don't want to close the door to other approaches, because we are seeing this is a very active area of research, how to use these very large models in a good way. So there is stuff about efficient fine-tuning, about adapter, about prompt tuning, and we want essentially to keep these emergent possibilities open. We don't want to build an architecture that will not have all of these kind of cool aspects. Okay, so we can talk a bit about scale, about the issue that we face with scale, some of the challenges that we see with scale. So the thing is that when you are training model with hundreds of billions of parameters, it's very unforgiving. You need excellent tooling, you need a scalable architecture, and as I was saying, every flop counts. A saving of a few percent is a huge saving in terms of compute budget for this kind when you are dealing with the scale. And there is a very interesting effect also kind of, which is that we know that very large models, their training tend to become unstable. So by unstable, I mean kind of what you are seeing here in this plot, which is on a 1.3 billion model, so not really the kind where you have the worst instabilities, but sometimes the validation loss just pops off and you don't really know why. And here, for instance, it doesn't really matter, it recovers afterward. But there are cases, especially as you go bigger and bigger, where it doesn't recover. And there has been discussion from the big group, some people of like, essentially like phase transitions, where when you pass like 10 billion scale, 60 billion scale, you start seeing more and more of these instabilities up to the point that they may completely prevent you from training your model. So some of these are numerical in nature because you are overflowing or underflowing the range that is allowed to you by float 16. And this, to an extent, can be avoided by going to like B316 on like TPUs or A100s. And hopefully we might be able to run the final training on A100. So that might actually be how we solve the numerical issues. But some of these instabilities are not numerical. For instance, the one I showed you here is not numerical. This does not come from an overflow or from an underflow. So it might be related to the data, for instance. And there is very interesting work from the DeepSpeed team on curriculum learning, where essentially having kind of like a schedule of showing harder and harder samples, starting with the easy one, prevents to an extent these instabilities. And then there's a question of how do you diagnose these instabilities? Because, okay, it's nice to see the validation plots, to see the loss explodes, but that doesn't really tell you what has happened. And so here there is tool with like the gradient nose scale. There is stuff like Weight Watcher, which allows you like to look at the spectrum of the weights, for instance, with some like much more mathematical tools. What is very interesting is that all of this is an open question. And I was saying earlier that the big models have very little literature on them. They are not really trained in the open. And especially no one talks about instabilities. Like this is people don't write paper about this, essentially, very sadly. So we are kind of the first to go into the open and we'll share our findings and everything. So this is quite interesting. To explore this, the engineering working group is doing these big exploratory runs at the 10 billion scale. So they have already done a 13 billion English-only model, and they are now looking at the 13 billion multilingual potentially for the second training. And these are very interesting ones where we learn a lot. For instance, we are starting to see that the dataset matters quite a bit. I will come back to this in just a minute. An interesting aspect of training very large model is that we don't quite train to convergence. We train to optimality. So essentially, if you look at the plots I was showing you before, you can see that there is kind of two regime in the training. There is the first one that is very efficient, but initially your loss is going down a lot for not a lot of compute. And then there is a kind of where you are reaching convergence and it's not really moving. And you can't really afford to train a very, very, very large model into this regime. Like this is not worth it. For instance, a 300 billion parameter model, you are going to start having convergence something like 5 or 6 times after you have done, like suffer 5 or 6 times the times of your optimality budget. And this is an underestimation because you can't really quite estimate precisely where convergence is done. So this is like what we are training is that we are going to be under training the very large model to an extent. And this is something to keep in mind in terms of the metrics. When do we evaluate our smaller models? Because we can train our smaller models to convergence. Some of the stuff that we do, for instance, in the training setup is batch size warm-up. So the idea of batch size warm-up is kind of like a learning rate warm-up, but on the batch size, you start with a small batch size, you linearly increase. The intuition behind this is that the gradient noise is very high early in the training, so you don't have actually much information in the gradient, so large batch size is a complete waste. And essentially, when you plot this in like this kind of scaling law plot of like the loss against the compute on the log scale, you see that we have this blue line without warm-up, this orange line with warm-up. You see the scaling is essentially the same. They behave more or less the same, but one of them is shifted quite a bit to the left, which is good. It means that the compute budget is cheaper. So this is a good thing to do in our training setup. Scaling laws can also be used as a diagnostic tool. So I was discussing a bit before about the first big run of BigScience, where we have this, I said disappointing, but actually I shouldn't try disappointing. I don't think it's a good way to describe it, because the goal of this run was mainly to test engineering tooling, not to get the best few-shot performance out of it. So actually it worked in this regard. So, but what we see is that the few-shot performance of the big training, of the first big training of BigScience, is not as good as what GPT-3 of OpenAI or what EleutherAI has been reporting. So these are results obtained by Stella Biderman using the EleutherAI NS on our first run. And we are more in line with the 2.7 to 6 billion model. And this kind of raises a big question, which is that a data problem or is this a problem with our setup? If this is a problem with our setup, we have to find it and diagnose it. If it is data, this is normal because for this first run, the data working group is not finished yet. So we just went with out-of-the-box Oscar. And we know that this is not as good as some of the state-of-the-art data set that exists, like the Pile, for instance, which has a lot more, let's say, curated content that is more interesting and that is also more advanced language, and that is better for the model to learn more interesting stuff and to be eventually better. So data matters a lot. And we can use scaling laws essentially to plot what's going on between 1.2 billion baseline and 13 billion. And we can see, and I'm going to do something very unscientific here, I'm going to tell you that this looks okay. But we are just doing this currently right now in the ongoing days. So that's all I can do. But what we are going to be actually doing this week is that we are going to plot the scaling law properly with like smaller models than the 1.3 billion, and to look if the 13 billion fits in the trend, because we are training on the same data set and everything. And if it fits on the trend, this means that essentially things are looking okay, and it's more of a data problem probably. This is the idea. So the second challenge that we have, and I'm going to go over this one quickly to let Yves talk about architecture, and also because multilinguality, we are just getting started, is that we are training a multilingual model that we want because we want it to be valuable worldwide, essentially. As I was saying, it's under explore at scale, and one of the significant challenges is that there is no high-quality multilingual datasets that is curated like the pile or the dataset that OpenAI has built for GPT-3. So this is something that BigScience is working, and that is really important. And the evaluation is also more challenging. Something that we are really excited to be doing is to look at this under the angle of scaling laws. So to establish essentially multilingual scaling laws, to quantify like how different like the languages scale differently. We think they do, but we can confirm this. We can quantitatively say, okay, how much one language benefit to another. So for instance, how much a token of English is worth for French. And this has been done actually in the past with scaling laws for multimodal setup to say, for instance, oh, an image is worth like that many words. So we can do something similar in a multilingual setup. And we can connect this to like fundamental linguistic work and validate our finding. And kind of the big dream behind all of this is to have a more principled multilingual setup to inform like sampling strategy and everything. So this is something we are starting out. Actually, we are starting probably with a multilingual one this week, and on which we will have interesting result to follow. So now I will let Yves talk about the architecture aspect, which is the last challenge that we are facing.
Thank you, Julien. I'm sharing my screen. Julien, do you mind sharing your screen?
Yeah, no problem. You can tell me when to pass the slide.
Yeah.
Yep. Oh, sorry. I was launching the presentation, but I didn't share. Yep. And I want this at the bottom, and let's go. Yep.
Okay, that looks great. Thanks. Yeah, so the third question, or the third challenge, or third open question that we are exploring in this project is what architecture to use. So in general, we are following the GPT-3 architecture, but with some changes. So one of them is the pre-training objective. And if you read the T5 paper, there's this interesting table that compares autoregressive language modeling with encoder-decoder architecture with prefix LM pre-training objective, and the results. And the results show, if you compare the first row with the fifth row, the results show that encoder-decoder models are much better than autoregressive language modeling. But at the same time, the last row shows that prefix LM is doing reasonably well, and it is much closer to encoder-decoder models than autoregressive language modeling. And there are engineering advantages for using autoregressive language modeling and prefix LM, and we'll talk about that in a minute. So this is one potential change in the pre-training objective that we are considering. The other one is other architectural choices, like which position embeddings should we use, which activation function to use, stuff like this. Next. So let's start with talking about the prefix language modeling. In the left figure, this is how the encoder-decoder model looks like. The input, let's say the input is I, am, and the output, the model will output encoder-decoder, end of sentence. It's the typical architecture with encoder blocks and decoder blocks. In autoregressive language modeling, you are only using decoder blocks, or like this is a decoder only model, and you feed the input tokens in the input. The model predicts them. Then basically you decode the output left to right. So when the model generates the token language, you take that word and feed it again in the input. Then the model generates the word model, and you feed that again in the input, and then the model generates the end of sentence token. Prefix LM is very similar. It's the same architecture, but it's just a difference in the attention pattern, or there's difference in which tokens get access, which tokens see which token. Next slide. Yeah. So here's what I mean by chain differences in the attention pattern. In encoder-decoder model, all the input tokens can see each other, and all the output tokens can see all the input tokens. In autoregressive language modeling, every token, even the input tokens, can only see the previous tokens. So when the model is encoding the word am in the input, it can only access the word I, which came before it, but it doesn't have access to the word a, even though it is part of the input. Prefix LM fixes this problem, where all the input tokens get access to each other, they can see each other, and then you decode the output in an autoregressive fashion. So why this is useful? Why this is advantageous? Because when the model is encoding a token in the input, it can develop, or like it can do a better job encoding this token given the following input tokens. Like you don't gain much when you restrict, like when the model is encoding the word am, or the word, let's say, when the model is encoding the word I at the beginning of the input, you don't gain much by restricting the model to only see itself. The model ends up learning a better representation for the input token I when it knows that the following tokens are am, a. So that's the intuition why prefix LM might lead to better results compared to autoregressive language modeling. The way you implement this is you, at training time, you select a random length for the prefix, and everything else is the same. The caveat here is that the results in the T5 paper are for a small model and for a fully fine-tuned model. So we are exploring, basically we are evaluating this, but we want to confirm that it works on a larger scale, like 1 billion token, 1 billion model size or even larger, and evaluate it on the few shot setting, not the fully fine-tuned setting. Next. The other architecture change that we are considering is the position embedding. So recently there has been a few interesting position embeddings that supposedly work better than the standard sinusoidal position embedding or the standard absolute position embedding. And some of the two recent ones that we are considering are the rotary position embeddings. Lots of people have evaluated it, and it works better than sinusoidal position embeddings at a very small cost and speed. And the way it works is that it injects positional information in every layer, not just at the input, and do that it embeds this information in the keys and queries of the self-attention layer. Alibi is even more recent. It's like a couple of weeks old now. The most interesting thing about Alibi is how well it does extrapolation. By extrapolation, I mean you train your model on short sequences, and then at evaluation time, you can use much longer sequences. And like we were hoping that the existing position embeddings do that, but this is not actually the case. And the paper shows this very clearly. So with Alibi, you can actually train a model on a short sequence length and evaluate this model on a longer sequence length, or you can train it on a long sequence length and then evaluate it on an even longer one. Implementation-wise, it's very simple and very fast. It's just an additive bias to the attention score. And similar to the rotary position embedding, it injects the position information in every self-attention layer, not just at the input. Next. So we evaluated the three position embeddings: alibi, rotary position embeddings, and sinusoidal position embeddings. And these are the results. And you see that rotary and alibi are consistently outperforming sinusoidal position embeddings. So this is promising. The difference between rotary and alibi doesn't seem to be that huge, but this is still interesting nonetheless. Two caveats here is that these results, similar to the prefix LM results, these results are on a relatively small model, the 350 million model, and we should confirm that we see the same results when you use much larger models. The other caveat is that this is language modeling loss only, and we should make sure that these embeddings work for the few shot setting as well. Next. Okay, so here I would like to summarize what we finished so far and what we are going to do next. So we are done implementing all the candidate architectures and all the model choices that we talked about today: prefix LM, alibi, rotary, all the stuff that we were talking about. We are mostly done with those. We are done pre-processing the multi-language training data. We have the English-only baselines, and we have the English-only evaluation benchmark. And the immediate next steps is debugging the 13 billion run. Julien mentioned some of the issues with that run, and still not clear what the problem is. So one of the immediate next steps is to explore this model and try to understand what's wrong with it. We would like to evaluate the English-only baselines that we trained on downstream tests, so instead of just language modeling class that we have been using so far. Start training and evaluating the multilingual model. So we have the data, we have the code. It's just a matter of starting these experiments. And the same applies for alibi, rotary, embeddings, and prefix LM. Start these training runs. We have the code and data and the setup. We want to start the training jobs and then evaluate the models when they're done. Next. And with that, I will conclude with encouraging you to joining us. So we have a long list of bite-size tasks that people can help us doing. You will gain interesting experience, and you will be very helpful for us. If you are interested in joining and helping us, you can sign up from the BigScience website. You can look at the list of tasks and issues that we are trying to address right now in our GitHub repo, and we meet on Wednesdays morning Pacific time. And I will conclude by thanking the people who actually did the work, so who actually ran experiments and wrote code and these things, and yeah, did evaluation and pre-training and prepared pre-training data. So these are the people who actually did the work. So thanks to all of them. And that's all I have. Thank you.
Thank you very much. This was really awesome. Thanks to the two of you. Before continuing, we're going to make a short break, and we are coming back in 2 or 3 minutes at the same YouTube link. So don't leave the YouTube link. See you in 2 or 3 minutes with the next talk. Okay, so while we wait for Percy, for our next speakers, Tom is going to give a few updates on some of the recent news that we got.
Okay, yeah, thanks, Matthias. Am I live? I'm not sure. Are you still live?
You are live, I believe. Yes.
I'm live. Okay. So a few updates on what's happening in BigScience. So generally, we got the confirmation that we have the whole compute that was requested, which is, if you have not been following, 5 million GPU hours, which is quite a significant compute budget. The other nice news is that in 2 months, we are planning the next live event where we'll share what's been happening over the fall. And this will be co-located with NeurIPS this time. It will be one of the social gathering of NeurIPS. And things, as you've been able to see here, right, a lot of things are happening. So we expect that in December, we have a lot of news to share. But until then, we still have this a few things to share today. So the next talk is going to be by Percy Liang. Sorry, my cat is all over the place. Percy will talk about what's happening at Stanford. This is an initiative that we've been talking a lot. We've been exchanging a lot, good practices, and basically we have so many things in common that it made a lot of sense to get them to talk today. And then we have the Gather Town. So if you want to know the links about the Gather Town, right, just go ahead, just go to the website page. Percy, I think it's the floor is for you now.
All right, let me share my screen. Thank you, Thomas, for that great introduction. Okay, let me just try to find it. Okay, I am going to assume that everything is up and running unless I hear otherwise. So I'm really happy to be here. Thanks again, Thomas, for giving me the opportunity to speak. And also, as Thomas said, we've been in touch a bit. And a lot of what I'm talking about is actually quite inspired and related to the BigScience effort, as we'll see. So I'm going to spend this time discussing foundation models, which is this term that we've been using to capture all the excitement and fear around these large models that we've been seeing, and discuss a little bit about the interdisciplinary center that we've created at Stanford and what we hope to do there. So right off the bat, I want to address a common misconception. I use GPT-3 often as an example of foundation models, and people immediately think large language models. But I want to emphasize that foundation models are not just large language models. There's a broader class of models that include things like DALL-E, which can generate images from text, as well as CLIP, which embeds images in a textual space. And just a little bit of a kind of personal background. My students and I have been working in this area of robust machine learning for a few years now, and which is how to get ML models that are trained on one distribution to do well in another distribution. In other words, distribution shift. And so CLIP was really impressive to me because it had zero-shot capabilities that matched the supervised ImageNet model, which is trained on 1 million examples. But moreover, it was actually much more robust on a wide range of other semi-adversarial alternative data sets compared to one that had been just trained on ImageNet. So this was really one of the reasons I got into foundation models, because of its promise for solving the kind of robustness problem. So let me start with a definition. It was really hard to kind of come up with a good definition of foundation models. So this is kind of the best we have right now. GPT-3 is kind of like the old story of the blind man and the elephant, right? Many people see different aspects of it, maybe capabilities, like in-context learning, or whether they're able to generate text, or whether they offer good embeddings. And the part of the elephant I want to kind of focus on for foundation models is captured by this definition. So foundation models are models that are trained using self-supervision on broad data and can be adapted to a wide range of different tasks. So it's this kind of train once and multi-purpose aspect that I want to highlight. And in some regards, BERT is maybe more prototypically what we call a foundation model than GPT-3, even though GPT-3 may be larger and more capable. So another way to think about foundation models is with two words, emergence and homogenization. This we talk about quite a bit in our report on arXiv that we put out last month. And so I'll begin with emergence, right? So GPT-3, let's go stick with that example for now, is just, these technologically, foundation models aren't anything new. They're based on decades old idea of self-supervised learning. And just very quickly, the way I think about self-supervised learning is you take a lot of raw data, text or images, and you make up little exercises. So for GPT-3, it would be predict the next word of a sentence. Then you train a powerful neural network, usually a transformer, to solve these little exercises. So it's like weight training, I guess literally. But by doing these exercises, the network develops the muscle to recognize an immense array of patterns and abstractions based on the data that it's given. So now you do this at scale. For GPT-3, it's 175 billion parameters. And what emerges is quite surprising. So you've probably all seen how GPT-3 can generate fluent text and code. But the thing that really struck out at me was the emergence of new capabilities, such as in-context learning. So you're able to give GPT-3 a description of a task that it's never seen before, at least in its exact form. And it can often do a surprisingly good job at it. So if you take a step back, this is not the way that machine learning is supposed to work as we were taught in school. So sometimes we can barely get ML to generalize to new examples, which is why I have been so interested in the kind of robust machine learning. But now we're talking about completely new tasks. And this emergence is what excites me and kind of freaks me out. So, in engineering, you generally design and build a system to do something, for example, translate sentences. But with a foundation model, it's kind of different. You build a foundation model, and then you go in and discover what it can do. So it's kind of more like scientific discovery. And this suggests that we've probably uncovered only a tiny fraction of the capability surface of these models, of existing ones, let alone future ones. So the other word I want to emphasize, which I think harks back more to the definition of foundation models, is homogenization. So this aspect is more, I think, of a sociological one, but maybe even more important in some sense. It used to be a case, using NLP as an example, that every task would essentially be its own subfield. You have a subcommunity of people who are working on building question answering systems with their own set of bespoke methods and data sets. You have the people in translation working on translation with their own bespoke methods and data set, and same for parsing, sentiment, and co-reference. But the story of AI has been kind of one of homogenization. With the rise of machine learning in the 90s and 2000s, we had the homogenization of a methodology and algorithms. So the whole idea of collecting a data set and training it to minimize some loss function. And then with deep learning, we have homogenization of model architectures with LSTM, CNNs, and especially now with transformers. And now with foundation models, we have homogenization of the model itself, where we have a foundation model that's not trained for any particular task, but can be used to a wide range of downstream tasks by either some sort of adaptation or fine-tuning. So it's kind of remarkable that every single state-of-the-art NLP system I can think of uses some form of foundation model today, and this just happened about 2 years ago. So, now we could refer to these models still as pre-trained models and self-supervised models or language models, if the models are of language. But we felt like none of these terms highlighted the kind of gravity of the situation, the foundational role that these models play in building AI systems. And I want to say right off the bat that, when I say foundation, I'm not suggesting it's a good foundation, or even that AI systems should be based on these foundations, or that these are somehow the foundations of AI as they're often kind of misconstrued to be. So it's well documented that these models have lots of problems. I won't go through I'll go through this very quickly because I think people know this by now. They lack common sense. They lack kind of internal consistency. If you remove a comma, then these models actually break down. And these are not one-off examples. They're pervasive. So existing foundation models, despite their impressive capabilities, still display a really profound lack of understanding when you inspect them closely. So it's interesting that these models are helpful for robustness, but they're not robust in themselves. So the dangerous part is they seem like they understand. So I think we might get lulled into a false sense of security here. So perhaps a bigger worry with foundation models and AI technology more generally is the harms that they might inflict on society, and especially on marginalized populations, which always get hit the hardest. The behavior of GPT-3 is ultimately shaped by the data that it's given, and it's not surprising that GPT-3 will generate offensive content. It can unintentionally generate untruthful text, and it can also be used intentionally to generate untruthful or simply non-falsifiable text that can be used for disinformation. So today we see big tech companies all developing their own foundation models and deploying them at scale. There's also overseas efforts and a few startups. And we have, these foundation models have a lot of raw potential, as we've seen. Because of the emergent behaviors, though, they're very hard to understand or control. So I should say that these raw foundation models are not or should not be directly exposed to users. They need to be adapted to a task, and generally there should be precautions that are taken, but these measures are far from bulletproof. And I want to stress the point that foundation models we talk about deploying foundation models to users, but usually this is done in a kind of more complicated machine learning ecosystem. So given the huge amount of interest and economic incentive and to deploy these models, and also the lack of norms and regulation, their pervasiveness will likely continue to grow. So I think it's urgent that the community acts now to ensure that they develop in a way that promotes social benefit. So sadly, though, it's becoming harder and harder for the entire community to engage. So stepping back, a big but underappreciated factor in driving the deep learning revolution was the open culture and the open ecosystem. It's become the norm that researchers release their data sets, code, and tutorials so other people can build on top of them, which I think has been largely responsible for why we've had so much progress in the field. But with foundation models, this openness is being eroded. So some models like GPT-2 and T5 are public, but the code for training them isn't. And GPT-3, well, it's not public and only a few people have API access. So openness is such a basic requirement for scientific integrity. It's what enables the community to collectively critique and validate and build on top of each other's work. I do want to highlight that there are two important efforts in the community, which are represented at the workshop here that are promoting openness. First is EleutherAI, this grassroots organization that has released the pile and a carefully curated data set of English text. And they've also managed to train GPT-style parameters models up to 6 billion parameters. So you'll hear from Stella about this. And the second effort is, of course, Hugging Face's BigScience project, which is one of the kind of key points of inspiration for us. And as I mentioned before, there's a lot of interactions and opportunities for collaboration here. So of course, openness is necessary but not sufficient. Training these large models still requires huge amounts of engineering expertise and lots of compute, and makes them out of reach for less well-resourced organizations, especially the ones that are trying to open things up. One interesting thing is that startups such as AI21 are still able to train the largest models today. But based on the way things are trending, it's unclear that this will remain the case. For example, building your own search engine these days is incredibly difficult even for a startup. So why is accessibility so important? Can academia just take and work on methodological improvements on smaller models and have industry just take these and deploy them? Or just take existing large models such as Roberta, you can download it and analyze it. And I want to argue that this is not enough. So first, the emergence property of foundation models, that means that you'll just miss important things if you work at smaller scales. So if you're working with a 1.3 billion parameter GPT-3, it doesn't look like in-context learning is working at all. It only happens when you scale up. After all, self-supervised learning has been around for a long time, but I don't think anyone would have predicted the kind of far-reaching impact it has today without scale. So secondly, just having a model that you can access fundamentally limits the types of questions you could ask. Machine learning is about the process by which we take data and model together and how they work synergistically to produce, sorry, when I say model, I meant model architecture, such as a transformer, how they work synergistically to produce a model with certain types of behaviors. So to study and to fundamentally improve on the status quo, you need to be able to study this process by changing the data, changing the architecture, and measuring what happens, not by using someone else's model. And as we've seen, the robustness and bias problems posed by these models run deep. So one really needs to reimagine these foundations from scratch. But again, doing this requires a large number of resources. So we're facing some pretty serious technical and social challenges regarding foundation models. There are not even, I think, right answers here. So we definitely don't want a few organizations, even well-intentioned ones, to kind of dictate where this technology is headed. There's basic questions that we don't agree on as a community. When is a model safe to release? Should we be filtering out toxic content before we train? What should you be reporting about foundation models in the way of kind of model cards? Should we even be building these foundation models? So to answer these questions, we need input from a diverse set of voices. We need representational diversity, especially from marginalized groups. Excuse me. We want institutional diversity from not just companies, but universities, nonprofit organizations. And finally, we want disciplinary diversity. So given the highly socio-technical nature of these foundation models, it can't just be only AI or computer science researchers. We need experts from law, political science, economics, information science, sociology, and so on. And the need for interdisciplinary diversity is what really prompted us to create the center at Stanford. So, excuse me. Last May, GPT-3 came out, and this was, in some sense, the most surprising. Excuse me, I have a cough. GPT-3 came out, and it was one of the most surprising results I've seen for a while. But of course, this was during the middle of the pandemic, and with 2 kids at home, I couldn't really do anything about it. So in October, I hosted a Stanford Human AI Institute hosted a workshop which included researchers from Stanford and OpenAI discussing various aspects of these models. And Jack Clark from OpenAI at that time said that universities should be building these models too. And that didn't really even cross my mind initially, but that kind of triggered a moment for me. We discussed it among the NLP faculty, and then I brought it up with Fei, and this was asked whether this would be something I would be interested in, and she was very enthusiastic and encouraged us to kind of think big. So even though we had started with GPT-3 as the initial instigator, we quickly broadened our scope because it was clear that Stanford key strengths was not in engineering and replicating large models, but to tap into the wide range of expertise across all the disciplines at Stanford. So the Center for Research on Foundation Models, CRFM, has 2 main thrusts. One thrust is building infrastructure. So we want to build tools and expertise for training these large models that could support a wide range of research projects, not just at Stanford, but the entire community. So we formed a small team of students and postdocs. And our first concrete milestone was just to replicate GPT-2. But I should emphasize that our overarching objective is the process, not the final model. We want to make this training accessible by releasing open source tools so that a lot of different domain experts, not necessarily from AI, can train their own models. And we also wanted this process to be reliable. We saw that these models are often unstable and training diverges, and we want to kind of understand the science behind them and make this process much more turnkey. And just a kind of a snapshot of where we are today. So we have released Mistral, which is our code base built on top of Hugging Face, which includes tools and scripts that helps one train these large models. And so far, we've released a lot of different dense checkpoints of GPT-2 medium runs with different random Cs. All these checkpoints are in Hugging Face's model hub. I've almost integrated all the stability features that we discovered, which were necessary, into the Transformers code base. And going forward, we're collaborating with BigScience engineering and trying to figure out how to incorporate the Megatron LM optimizations into Transformers. So we could have gone with Megatron LM, but we decided to go with Hugging Face because of the rich community that Hugging Face already has. And this was a better fit for kind of our initial goals of making it open and usable as opposed to performance first. The second thrust is building community. And we realized that there were a lot of folks at Stanford already interested in working on these foundation models. But they might not have been talking to each other. So there are people who were working on parallelism to scale up models, theoretical understanding, building video models, studying the bias of these models, disinformation implications, economic impact, applications for law and healthcare. And so we thought it would be very productive for everyone to talk to each other. So together with my student Rishi, we started a community at Stanford so that people can just get to know each other's work. And we drew inspiration from BigScience. If they can bring together the whole world, surely we can do something more modest at Stanford. So at the end of March of this year, we started having weekly meetings just to get to know each other. The community grew, and now it has over 175 students, postdoc, and faculty spanning 10 different departments. Each week we had breakout rooms, spotlight talks, and we have an active Slack. And for me and many others, it was very eye-opening to learn from all the different people with different from different disciplines. For example, I had a lot of great discussions with Rob Reich and Katie Creel on how to think about ethics in the context of foundation models. So there was a lot of energy in the community, and over time, we got more conceptual clarity about how to even think about foundation models, which I mentioned was, coming up with a good definition was actually kind of challenging. So one of the first things we did after having these discussions was to write a report. So this was a bit of a crazy idea, and I didn't know if it was going to work. Could we get all the people in the community to come together and write one report that attempted to cover as many aspects of foundation models, at least that we had expertise for? I figured, well, if the experiment failed, there would be no report, but at least people would have gotten to know each other better and learned something. So we laid out 26 sections ranging from applications like healthcare and law, and to technology like systems and theoretical understanding, to societal issues like inequality and misuse, environmental impact, and so on. And we just had people sign up to sections that they were interested in, and eventually each section had a student and a faculty lead. So this actually worked out pretty well. Within each section, we had people from different research groups now coming together to learn from each other. But we also got sections to talk to one another across sections to help the report become more of one cohesive whole rather than 26 independent sections. And we released this report on arXiv. You can go read it. If you don't have time for reading a 200-page report, I think the introduction actually does a fairly good job of summarizing. So don't be too intimidated by the page limit here. So undoubtedly, there's a lot that we didn't cover, and we're revising the report right now and planning to release a second version. So if you have any feedback, please let us know. So I want to start concluding with a few thoughts. There is a wonder whether foundation models are inevitable. And the way I want to think about this is, the current path that we're on towards models that we don't understand, trained on massive amounts of unfathomable data, controlled by a few organizations, that part is not inevitable. I think there is still some kind of really useful and good element of these models, at least for kind of making more generalizable and robust systems, that I think we want to be able to kind of keep the good and improve things. So there's three kind of points I want to end with. First one, again, foundation models are not large language models. They started in text, just like deep learning started in computer vision, but now we have models, foundation models that are trained over a number of different modalities, and moreover, kind of multimodal models, which is natural given the homogenization here. Second is that this idea of training on just tons of data that you scrape from the internet is not inevitable. We should be thinking about the people who create this data and their rights and what value they're getting to what is responsible and allowable for curation and training, all the way to kind of what applications should be deployed. And I want to call out to Hugging Face's BigScience working group on data governance. We had a talk by Yassine and Meg earlier that explicitly kind of addresses this. So I think there's hope that we can improve the state of the art a lot more here. And then finally, the idea of having a monolith, a single organization that masses all this data together and training one model is also not inevitable. I really imagine a world where there's much more modularization and decentralization of both the training and the data. So efforts like learning at home are interesting here because they change the idea of how compute for these models could even work via volunteer computing. And I want to lean on Wikipedia or open source software as a kind of a model of how the future of foundation models could evolve, where there is much more in the commons, and it's the contribution to these models is much more of a community effort rather than an arms race between a few powerful organizations. So finally, I want to end by saying that we are still in the very early innings. It's incredible how fast these models have been developing. They're very deceptively simple. Self-supervising and scale gives rise to this emergence. And I think this emergence is what makes this future so uncertain. But one thing is for sure, the homogenizing quality of these models, we're starting to build our entire society's ecosystem on them. And the stakes are high here. So we could create good foundations, and then we can enjoy much more efficient and fair and robust AI systems. But we can also create very bad foundations, in which case we can end up in a very volatile state that exacerbates some of the harms. And so I think we all need to work together as a community to achieve the former and not the latter. So thanks for listening, and I'm happy to take questions.
Wow, Percy, thanks a lot. This was extremely exhaustive and deep at the same time. Thanks so much. I will just abuse my position as chair and dare a very small correction. BigScience grew out of an initiative by Hugging Face, which is the main driving force, but it grew well beyond it. There are a number of different institutions which are taking part in it. I think one of the cool things is that the compute it's currently running on is a publicly funded supercomputer, which I think is an interesting thing that public funded infrastructure is having a comeback, at least in this BigScience. I'm sure that lots of people have questions and would like to engage. I would invite those people to hold for 30 minutes their question comments for the Gather Town later on. And before we do this Gather Town and interactive session, we have one last talk by Stella. Stella has a double role, though during the day, Stella analyzes international relations and geopolitical conflicts using ideas from social networking and machine learning. And then, I'm not sure if during the night or the other half of the day, Stella is one of the co-leaders of EleutherAI, which was mentioned by Percy. EleutherAI is one of the most exciting groups in AI, in my opinion. You've certainly heard of the Pi, or GPT-Neo, GPT-G, which were all created thanks to that grassroots initiatives. And like reading out this bio makes me realize that this could be a great bio of a superhero, Stella. So we are very happy of having you and for your willingness of sharing some of your insights and conclusions in participating and in leading EleutherAI. So it's all yours, and we are looking forward for this.
Thank you very much for that introduction. Let me figure out how to use a computer for a second. Can you all see my screen?
Yes, we can.
Okay, excellent. Don't actually know how to put this in presentation mode. My apologies. There we go. So hello, my name is Stella Biderman, and I am one of the leaders of an organization called EleutherAI. And a little bit about us. So I am a mathematician, a theoretical computer scientist, and recently more and more a AI alignment researcher and AI ethicist. A lot of the conversations we've had today have focused on how it's important to make sure that these powerful models are aligned with human values. And that's something that I've grown very much invested in working on and am very excited about. EleutherAI is a decentralized, which is a fancy way of saying poorly organized, grassroots collectives of researchers that work on AI alignment, scaling, and open sourcing AI research. And as there we go. So I'm going to tell you a bit about how we got started and our work on large public language models, then talk a little bit about AI alignment and kind of the ethical implications of these models, and then go over some of our other very exciting, though less well-known projects. So we straight up started as a joke in a Discord server. Connor Leahy is someone who was one of the first people to release open source, release replications of GTB2 back when it came out. And he was hanging out in an AI Discord channel and said, hey, let's try to replicate GTB3. And that's basically how things got started. They start off as a couple of people hanging out in a Discord channel. Now we're about 9,000 people hanging out in a Discord channel. So our community is organized via Discord. We have a heavy focus on transparent research. One thing that Percy talked about was how there's a lot of the research is not really released anymore. A lot of things are kept very closed up, and that's something that we found both ethically problematic and also pragmatically problematic as we start to work on large language models and other projects. So we put a very high focus on transparent research. You can stop by our Discord channel and listen to us talk and listen to us make our plans on various projects. Our code is almost entirely public while it's being developed and while it's being released. And we believe that there's an importance in doing successes and failures in public. It's very community driven. I mean, we started off working on language models, but we've branched out as more people have joined and wanted to get involved. Basically, people can pitch whatever projects they want, and projects get started because people really want to focus on making them happening. There are all sorts of things I would have never learned about had people not come to me and said, hey, I have this crazy cool idea. Like, do you think that we could somehow find computing resources to do it? And it's not just doing research. We have, as I said, about 9,000 people on our Discord channel. About 20 of them actively participate in our research. We have a lot of conversations about the current state of the art. So we often have people who drop by to talk about their research. Ophir, the guy, one of the authors on the Alibi paper, came by the day after his paper got released. One of the engineers from Hyperclova came by and talked about kind of the problems and issues that they had to deal with the day that they announced their model. So it's a cool place to talk to people who are really at the cutting edge of research. And we have reading groups. So we have an interpretability reading group right now. We've talked about setting up some more if there's interest. So the thing we're best known for is our work on language modeling. So when we got started almost exactly a year ago, the largest public model was GTB2, 1.5 billion parameters, but larger models had been announced as existing. They just hadn't been shared with the public, most notably GTB3. Another big issue was that there weren't really any public language data sets so that were large enough to train these models on. So there were large data scrapes that you could download. For example, the Common Crawl, but there's a lot of different issues involved in training a language model on the Common Crawl, and we felt that really wasn't suitable for what we wanted to do. There was almost no public information about how to do this kind of work. You basically had the contents of the GTB3 preprint, which was sparse in some details and had some extremely important information and footnotes. And so we, to a large extent, felt like we were having to figure things out as we went without much of a guide. And what we were doing was widely believed to be infeasible. I mean, you've probably heard for close to a year or two now that these models are absurdly expensive, that these models are inaccessible. And I mean, I'm not saying that's not true, but I think that some of the hype around the models has expanded to include hyping up the extent to which they are infeasible to train and feasible to build. And I might complain about that a bit later. And yeah, people straight up told us we were crazy. So what have we done since, what have we done since then? So we've trained 3 large language models. The first 2, which we call GTB Neo, are 1.3 billion parameters and 2.7 billion parameters. They were good proofs of concept, but somewhat mediocre. They, for example, did not meet the performance levels of the comparably sized GTB3 models. And it was really a learning exercise. That was the first time anyone involved in the effort had done anything remotely on this scale. And we learned a whole lot while kind of organizing and building things. And then we released GTBJ, which at 6 billion parameters is, until the BigScience project releases their first couple models, at least currently is the largest freely available autoregressive language model. We've released the Pile, a curated data set that we went out and just built for ourselves. And since then, we're really thrilled to see that there are other large data sets suitable for training language models on. So one of the most exciting things, I think, in terms of data quality after the Pile was that C4, a large language data set that had been used to train models in the past, but which hadn't actually been released to the public, was released. That was the work of that was a lot of work put in by people at the Montreal AI Ethics Institute. And they tried to document the data set, and they really lobbied to get it released. And I guess we're no longer underground. Usually when talking about what we do, I say that we're an underground research group, but I guess now that I'm here giving this talk, it's probably not an applicable moniker anymore. So one of the big questions that we get, both historically and currently, is why release these large language models? This is something that we've kind of talked about throughout this talk. People are worried about the impacts and dangers that these models can have. So why train them and release them to the public? Also, I want to be clear from it that right now I'm speaking on the behalf of EleutherAI. BigScience and EleutherAI have a lot of similarities and a lot of agreements. BigScience's attitude towards release norms for AI models have not been fully developed, and I do not take this to be a promise on the behalf of the BigScience workshop as a whole. This is mostly my opinion and the opinion of the people at EleutherAI. So first of all, we think that there is a significant amount of important research that can only be done with access to these models. If you really want to understand how these models work, how these models fail, you need to be able to actually put them in the hands of people who did not develop them and people who have incentives to see them fail. One thing that we've seen is that large organizations have a tendency to censor or modify research that is critical of them. We've seen this at, Google's been in the news for this a lot recently. They fired a lot of their AI ethics researchers over disputes about large language model use. Internal emails at Google have leaked that have indicated that they have edited the choice of language to talk about and frame conclusions about the impacts of computer security research. And so we really think it's important to put these models out there and put them in the hands of.
Try going to assistant settings, then checking your voice match settings.
My apologies. I probably can't refer to the G company by name anymore. Where was I? Yeah, so we think that there's a lot of important research that can only be done once you put these models in the hands of people who want to break them. We think that most of the harm was done by GTP3 the day it was announced. The day before GTP3 was announced, feels like forever ago now, but people really didn't believe that scaling was particularly important. Like GTP2 was larger than any previous autoregressive language model. It was a little bit bigger than larger models like BERT. But the idea that scaling equals power or scaling equals intelligence, as you're starting to see many papers claim, was not something that was really widely discussed, let alone widely accepted. And we think that announcing GTP3 and kind of letting the cat out of the bag that actually, if you just build it bigger, it gets way better, was to a large extent the biggest secret the biggest thing in terms of keeping this technology out of the hands of people who want to use it to do bad things. And finally, delaying the release of language models is not a solution to disinformation. It's not a solution to distrust in the media or in the internet content. This is a really big topic politically in the United States, and I'm sure around the world, where people are talking about how we're never going to be able to trust things on the internet. We're never going to be able to trust people that we're talking to with deep fakes. And there are real problems to be addressed here, but delaying the release of new technologies is not an actual solution. At best, it's a patch, but we don't really think that that's a good reason to not release technology, especially when there is a lot of good that can be done by putting these models in the hands of safety researchers, of ethics researchers, of computer security researchers. So I've mentioned safety or AI alignment a bunch recently. So there are a couple different ways you can look at the the safety issues involved with AI technologies. And at EleutherAI, we are largely focused on what I'm going to call the medium term. How can we prevent harm from future models? There's a lot of very good and very important work being done right now at BigScience, at Stanford, and elsewhere about how to mitigate the harms being done by the current generation of models, how to safely deploy them, how to get people to not deploy them when they would be dangerous. But that's not what we're focused on. At EleutherAI, the big thing that we're focused on is stopping the next big paradigm shift or the next big harm from catching us as much by surprise as the current generation caught us by. So one of the big things that we focus on in this regards is interpretability. We want to be able to really get inside language models and understand how they make decisions and why they make those decisions. One of the things that we're really excited about is prompting. The idea that you can use language models, you can prompt language models and use that to control how they behave or how they reason is something that I think is a very promising approach for controlling both the current language models and also future models, and as well as any kind of model that exhibits the sort of zero-shot behavior that GPT-3 and large language models do. As I'll mention in a bit, there are other models that exhibit the same kind of zero-shot behavior, and they can also be prompted. And finally, a big thing that we talk about a lot is kind of what changes at scale. How do things get better? How do things get worse as models get bigger? Because the cat's out of the bag. When you make models bigger, you make them more powerful, let's say. They can certainly do a lot more, and they can all of a sudden do things using the same training data that they had previously been unable to do. So we talk about a lot about language models, but that's by no means the only thing we do at EleutherAI. Probably the second most well-known thing that we've done is VQGAN Clip, which is a methodology for making computer-generated artwork. All of these images that you see on the screen right now were generated by a computer given the prompt of a string of text. So the model was asked to draw a garden, was asked to draw a monastery in a swamp. No, not a swamp. A monastery, I'm blanking on what exactly the prompt for this one is. A library, and so on and so on. And it really displays a gorgeous array of abilities and of and diverseness in its artistic style. Other cool artwork is clip-based diffusion, where you are making a diffusion model, but kind of using clip to guide the evolution of its gradients. On the left here, you see a painting called Before the Bath, turned into a zombie over time. And on the right here, you see a clockwork angel of air. And it says at the end there, trending on ArtStation. And this is one of the things that to me is most fascinating about these kind of text language combined models, which is that just like with GPT-3, with clip diffusion models and with other clip language models, they have a surprising understanding of what things that we don't think of as key to the caption of an image kind of mean. So we quickly learned that if you add trending on ArtStation, the quality of the image goes up. Or if you add rendered in the Unreal Engine, the Unreal Engine being a popular video game engine, you get kind of high quality video game graphics. And you can control both the quality and the style just by adding a short bit to the image description. And that is, I think, very much analogous to the way that you can use prompting to control language models. Other cool stuff that we're doing involves contrastive models, building new types of models analogous to clip, but with other kinds of modalities. So one thing that we're working on is storytelling. We are using a clip-like architecture to train a model that can understand critiques of stories and we've had a lot of success beating out prompted models as well as fine-tuned models of comparable size. This is something that have been working on for past couple of months, and I'm quite excited about. There'll be a paper coming about this pretty soon. And we've also had people working on using CLIP-like models in biology. So here, basically, it's the exact same concept as CLIP. You have a text description, it's paired with an image, except in this case, you have a text description and it's paired with a protein. So the text describes the structure, the properties of the protein, and the model has to generate the protein. And you can see that we're actually able to learn structural properties decently well. It's kind of hard to interpret these numbers in abstract, but 25% accuracy is pretty impressive given what we're working with, given what is being worked with here. And we have a lot of other stuff going on with biology research as well. One of the big thing that used to be the focus of our biology research group was replicating AlphaFold 2. AlphaFold 2 is a program created by DeepMind that blew people's minds when talking about protein generation and modeling protein folding. We got most of the pieces built. We got some good preliminary results. And then Google released AlphaFold 2. It is just out there online. You can download the pre-trained models. You can download code to fine-tune it. You can pay Google to fine-tune it on your own data. And so since then, there's been a bit of a reorganization as replicating the model, while still interesting, is less important now that the model is actually out there and freely accessible. So one thing that has been worked on is making models that are more accessible. And what I really mean by that is making models that are cheaper, because a lot of biology labs, including ones that are for biologists working with the state-of-the-art technology, do not have access to the same kind of resources that AI researchers do. So for example, I've spoken at length with the person who trained what is called Protein BERT. It's a model like BERT, but predicts protein sequences. And he was salivating when I mentioned offhandedly that I could like lend him an A100 for a day. Now that's way more compute than he really had access to when doing his entire paper. And there's this, in general, this really big disconnect. People talk about the disconnect between, the companies or organizations with the most resources and the quote unquote everyday people. At universities, at smaller companies who want to do cool research too. But there's a second gap between what in the ML world passes for someone who doesn't have a lot of resources, who is at a university or is at a smaller company, and what people who want to deploy these types of models in other domains have access to. So a lot of people who are really, a lot of organizations, they're really middle of the pack in the United States, at least in AI research, have way more resources than most biology departments, have way more resources than most social science departments. And that was really an eye-opening thing to learn. To an extent, it was something I was abstractly aware of, but by talking to people in the biological domain and learning just how important it is to kind of compress and make these models usable on CPU even, has been really eye-opening and changed the way I look at accessibility of research topics. And then as a final note, I'm sorry, still waking up a little bit, need some coffee. So as a final note, we have produced a decent number of research papers. People often like to see this list. Out of my own curiosity, if anyone knows what the record for most publications by a Discord channel is, I would love to know what that is. But here's kind of the work that we've done so far, and we have some really exciting things coming out in the near future.
Thanks a lot, Stella. This was very broad and inspiring, and I think lots of people would start joining your Discord channel after this. For the interactive Q&A for discussions, I invite everybody to move over to the Gather Town. The link is on the website of the BigScience episode 2. And we will be there for informal discussions. If you have specific questions, if you want to interact, if you don't agree with something which was said, this will be the right moment and place to share those things. So thanks a lot. We will conclude this after the Gather Town, so we won't be streaming again on YouTube for this episode 2. Thanks a lot for joining us today, and hope to hear and see many of you either on our Slack channel or on